In this lecture, I will discuss the numerical problem based on the attenuation. Attenuation is the transmission characteristic of the optical fiber. So, a numerical problem which is based on the attenuation is discussed in this particular lecture. In general, we define the attenuation, total attenuation in optical fiber by the number of decibels, that is denoted by dB, is equal to 10 logarithmic 10 P input upon P output. So if one have to calculate the attenuation, for that we have to use this formula. Number of decibels is equal to 10 logarithmic on the basis of 10 P input and P output, where P input is the input power, P out a P emerging and the power of the signal, so that is output power. So the ratio of input and output ratio can be written as P in P out is equal to 10 is basis this decibel number divided by 10. So this is the formula to calculate the input and output ratio of the signal by using this formula. So this formula is used to calculate the attenuation for the whole length of the optical fiber. So this is the first case, and the formula is very simple. dB is equal to 10 logarithmic of 10 at the basis of 10 is 10 P input and P output. And now the second formula is that attenuation is expressed in terms of decibels per unit length. The unit you can define decibel per kilometer, and the formula will be alpha dB, this is the length, is equal to 10 log at base 10 P input upon P output. This is our second formula for the attenuation. So there are two formulae for the attenuation. In first case there is no use of the length, but in second case we are using the length. So this attenuation is calculated for per unit length, and that defined in terms of the kilometer. Length is defined in terms of the kilometer. So loss of the signal per kilometer. So this is the second formula. In the first formula you have seen that decibel was equal to the 10 log at the base 10 and P input upon P output. So we have these two formulae for the attenuation purpose. Number 1 is number of decibels is equal to 10 this log at base 10 P input and P output. Second formula is alpha dB, that is attenuation. This is length is equal to 10 log at the base of 10 P input upon P output. So these are two basic formulae for the attenuation, and now the numerical problem. Question is, when the mean optical power launched into an 8 km length of optical fiber is 120 microwatt. The mean optical power at the fiber output is 3 microwatt. Right. So now you have to determine key part, the overall signal attenuation or loss in decibels. Through the fiber assuming there are no connectors or splicer. Connectors or splicer. So this is part A. Part B is the signal attenuation, per kilometer. For the fiber. C part is the overall signal attenuation. For a 10 kilometer optical fiber, using the optical fiber link, using the same fiber, with splices at 1 kilometer intervals, each giving an attenuation of 1 decibel, right? So this third part is this one. Here they ask into the question the overall signal attenuation for a 10 kilometer optical fiber link using the same fiber with splices at 1 kilometer intervals, and each splicer at 1 kilometer giving an attenuation of 1 decibel. And the fourth part, D part, is the numerical input output ratio, input oblique output power ratio. In case of C, the third part. So I am repeating this question again. The question is, when the mean optical power launched into an 8 kilometer length of fiber is 120 microwatt, the mean optical power at the fiber output is 3 microwatt. So in this statement, what is given? Given is this length, that is L, 8 kilometer, input power, that is 120 microwatt, and output power, that is 3 microwatt. So for this given statement, we have to determine number 1, that is A part, the overall signal attenuation or loss in decibels through the fiber, assuming there are no connectors. So as I told you that in the first part of the question, the overall signal attenuation or loss in decibels through the fiber, assuming there are no connectors. So it means for the first part you have to use the formula number 1, because in the formula number 1 or from the formula number 1 we have to determine the overall loss into the signal for the given optical fiber. And what is the value are given? The values are P input and P output. So with the help of that one can find out the loss into signal. So I am calculating the first part of this numerical problem, where these 3 parameters are given in the statement, and for the first part we have to just calculate the overall loss into the given length, that is 8 km. So the overall signal attenuation in decibels through the fiber is signal attenuation, that will be in dB is equal to 10 log at base 10 pi input and p output. So in the first part, that is A part, we have to just put the value of p input and p output, and that is equal to 10 log at the base of 10 120 microwatt upon 3 microwatt, and this is equal to 10 at log base 10 40, and the result is, when you will calculate this log 40 at the base 10, that is equal to multiply by 10 is 16 decibels. So the answer of the first part is 16 decibels. And in the third part of the question, the second part of the question, they ask the signal attenuation per kilometer for the fiber. Remember and note down this particular point, that in the second part they are asking about the loss in per unit length, in terms of the per unit length. So signal attenuation per kilometer, that means if you have to find out the loss or attenuation into the optical fiber for a given length, then that time you have to use this formula, second one, alpha, this dB into L is equal to 10, this log 10 P input upon P out, same. So this is 16 dB, the first part. And now the second part of the numerical problem. Now the second part, the signal attenuation per kilometer for the fiber, that will be alpha dB into L, and that will be, we have already calculated this factor in the first part, and that is 16 dB, 16 decibels. So alpha dB is equal to 16 decibel upon length is 8 km. So this is equal to 2 decibel per kilometer. So now the attenuation, signal loss for this optical fiber of the length 8 km, we have found that the loss is 2 decibels per kilometer. Right, in the first part we have just calculated overall loss into the optical fiber, And into the second case, second part of the numerical problem, the question was if we have to find out the loss per kilometer. Now the answer is 2 decibel per kilometer in the second case. So we have calculated two parts. In the first case we have found this total loss into that signal into that optical fiber of the length 8 km, where input power was this 120 microwatt and output power was 3 microwatt. And the first case the answer was 16 decibel, and into the second part the answer is 2 decibel per kilometer. So loss of the signal per kilometer is 2 decibels. Now the third part, and third part is a little bit tricky, where the question statement says that in the third part, the overall signal attenuation. We have to find out the overall signal attenuation for a 10 km optical link. Now the length is different of the optical fiber from the earlier two cases, and the material of the optical fiber, or you can say the optical fiber, now is almost same with the same characteristic as we have used in earlier two cases. So the overall signal attenuation for a 10 km optical link using the same fiber with splices. Now the different point is, now there are connectors with the splices or connectors at 1 km intervals. So this 10 km overall length is 10 km, but that 10 kilometer length of the optical fiber is made by some connectors, and each connectors have the length of 1 km. So overall in 10 km how many interval will be there? There will be 9. So there will be 9 connectors. This is the only point basically in this part of the numerical problem. So now in case of third, length of the optical fiber is 10 km. This is overall length, but the point is that this 10 km length of the optical fiber is made by the 9 connectors. There are 9 connectors, one each with 1 km interval. So if this is the length from it starts from A to B, this is 10 km. Right. So as I said earlier that we are using the same fiber with the splices at 1 km intervals, but each interval, each splicer, each connectors is giving an attenuation of 1 decibel. In addition to the overall attenuation of the optical fiber, each splicer also giving some attenuation, and that is of the order of 1 decibel. So this is the point. So first point is that we have to find out the attenuation because of the length of 10 km. Then they are saying that this in this optical fiber there are basically some connectors. So at 1 kilometer interval. So suppose this is 1 kilometer interval. So first connector is here. Second 1 kilometer, one connector is here. Third interval 1 kilometer. This is also 1 kilometer, 1 kilometer to up to here. So there are total 9. This is one interval, second interval, third interval, fourth, then 5, 6, 7, 8 and 9. Then it completes. So there are 9 connectors, and each connector basically provide 1 decibel loss into the signal in addition to the overall loss of the signal because of the total length, right? So first there are 2 points in this C part. One is this one, where we have to find out the attenuation of the optical fiber because of the total length, A part. And the second part of the numerical is in A part. Basically we have to find out the attenuation into the optical fiber because of the total length, right? That is the first step. So because of the total length, that is 10 kilometer. And the second point they are saying कि because of each connector there is a loss of signal 1 decibel. At 1 kilometer interval there is connector, and because of that signal loss, and that signal basically amount that loss is of the order of 1 decibel. So for each connector 1 decibel, here 1 decibel, for the third 1 decibel, for the fourth 1 decibel, 5, 6, 7, 8 and 9. So there are 9 connectors, and each connector basically loss the data of 1 decibel. So total loss is equal to 9 decibels. This is the point. This is the second part of this section. We are solving this C part of the numerical, and in this C part there are again 2 parts. One is because of the total length, the loss into the signal, and second is because of the connectors, because of the splicer. And each splice is at each interval we lose the data of 1 decibel. So there are 9 in 10 kilometer. There will be 9 interval, right, in 10 kilometer. So there will lose the data, we will lose the data 9 into 1 decibel. Total is equal to 9 decibel. Now what will be the loss of data in this 10 kilometer? That is the point. So we have seen earlier that alpha dB is equal to 2 decibel per kilometer, right? In the B part we found that loss of the data per unit length or per kilometer is of the order of 2 decibel. The answer was 2 decibel per kilometer. And into the C part we are using what? The same optical fiber. So we will use the same property. Means we have to use this answer of the B part, that is 2 decibel per kilometer. So we have used the same optical fiber. So length right now is 10 kilometer, and for each kilometer we lose the data of 2 decibel, right? Loss in signal is 2 decibel. So there are 10 kilometer, so total loss into the signal will be 2 into 10 decibel. So in 10 kilometer the loss attenuation will be equal to 2 into 10 decibel. that is equal to 20 decibel. I hope I have cleared this idea of the C part, because there was some trick to solve this numerical problem, right, by using the connectors. So each connector basically lose 1 decibel, and there will be 9 interval into 10 kilometer. If we are using one interval is of the 1 kilometer distance, right? So there will be 9 intervals, and at each intervals you are getting one splicer. So each splicer lose 1 decibel. So there will be loss into the signal 9 decibel, right? And into the first case, length of the optical fiber is 10 kilometer, right? So the loss to overall loss of the signal attenuation for the 10 kilometer distance of the for the 10 kilometer length of the optical fiber, that will be 2 into 10 decibel, that will be 20. Why I use 2? Because right now into the third part also we are using the same optical fiber that have the same characteristics as into the B part. So the loss, the attenuation will be same. So earlier we found that loss is 2 decibel per kilometer. So for the 10 kilometer, the loss into the data will be 20 decibel. In 1 kilometer, loss is 2 decibel. So in 10 kilometer, that will be 20 decibel. So now into the third part, the overall attenuation will be the first 20 decibel plus that 9 decibel. So answer will be 29 decibels. So the overall attenuation will be 29 decibel. So this is the point only in the third part. If we are using connectors, so that time we have to add the loss of the connector also, because of the connector also. And here we have mentioned that for each interval we have a connector, 1 kilometer interval we have a one connector, and the loss because of that is 1 decibel. So there are 9 intervals, so there will be 9 splicer, and for each, as I said earlier, loss is in 1 decibel, total will be 9 decibel, right? This is the second phase of the C part, and the first phase is that we have to find out the overall loss because of the 10 kilometer, and that is 20. So this 9 is additional to the this 20. So total will be 20 plus 9 decibel. So this is the point only in this part. So this is the answer. The loss, overall loss is 29 decibels. And now the fourth part, D part of this numerical problem is that we have to find out the ratio of the P input and P output, right? And in which case, the case is C. The statement of the numerical problem was that the numerical input oblique output power ratio in C. So we have to find out the ratio of power. So the D part of the numerical is the numerical input output ratio, input output power ratio in C is what? How much was the attenuation in case of C? 20 plus 9, that was the 29. So overall attenuation is 29. So P input upon P output, as I have used earlier this formula, that was 10 raised power dB upon 10 is equal to 10 dB is 29 divided by 10, and when I simplify it, the answer is 794.3. So the ratio between input and output power is of the order of 794.3. So these is some basic ideas to calculate the attenuation in an optical fiber. There were three cases actually. One was very simple, where one have to calculate the overall attenuation for a given length of the optical fiber, but there was no length considered. They asked just about the total attenuation. And into the second part of the numerical problem, what was the point? They asked about the per unit length attenuation. And into the third case, what they did ask, they asked that there are some connectors at a particular interval. So how much loss will be there? How much attenuation will be there? So in that case, we have to calculate overall loss of the signal and because of the splicer. So sum of these will be total attenuation into the optical fiber. And the fourth case was related to the ratio of the input and output power of the signal, right? So this problem was related to the optical fiber. I hope I have made my idea clear about the attenuation. If you found any problem related to, you can message me. Thank you.